Hello, Mr. W and students. My name is Marvelo, and in this video, we'll be talking about the First Lady of Physics, Chien-Shiung, a groundbreaking physicist whose experiments changed how we understand the laws of nature. Let's get right into a remarkable story. Physics has always sought symmetry, balance, and rules that never bend. Think about Newton's third law. For every action, there is an equal and opposite reaction. Force is balance. Motion conserves momentum. The universe, it seems, keeps its books perfectly balanced. But what if nature herself doesn't always play fair? In the mid-20th century, one woman stood before the scientific world and proved that one of its most sacred assumptions, that nature treats left and right equally, was wrong. Her name was Dr. Chien-Shiung, and through her brilliance, precision, and courage, she changed not only the laws of physics, but also the story of women in science. Chien-Shiung was born on May 31st, 1912, in Liuhe, a small town near Shanghai, China. At the time, opportunities for girls in education were almost non-existent. Despite this, her father, Wu Zhongyi, was a revolutionary and an advocate for women's education. He was an intellect and an engineer who founded one of the first schools for girls in China, the Mingde School, where Chien-Shiung was among the very first students. And so, from a young age, Chien-Shiung displayed an insatiable curiosity. She would spend hours reading about mathematics, engineering, and the mysteries around the natural world. In 1930, she enrolled at National Central University in Nanjing, majoring in physics, one of only a handful of women in her class. Her academic brilliance stood out immediately. After graduating in 1934, Wu worked as an assistant at the University of Zhejiang, but she yearned to study abroad. Hence, in 1936, she traveled to the United States enrolling in a PhD program at the University of California, Berkeley, which was the same laboratory where Ernest Lawrence had developed the first cyclotron. There, she studied under Ernest O. Lawrence and Amelia Segre, both future Nobel Prize winners. Wu's doctoral research focused on nuclear fission and beta decay, areas that would soon define her legacy for the future. At Berkeley, Wu mastered experimental techniques that few others could match. Her meticulous attention to detail and steady hand made her indispensable in a field where one small error can mean the difference between discovery and failure. During World War II, Wu joined the Manhattan Project, the top-secret U.S. program developing the atomic bomb. She worked on improving the detection of radiation and refining the process of uranium enrichment by studying how gases diffuse through barriers, a complex interplay of thermodynamics, pressure, and diffusion physics. And so her contributions helped the project achieve accurate measurements of radioactive decay, essential for both the bomb's construction and later for peaceful nuclear applications. Beyond her wartime research, Wu made so many lasting contributions, such as the contributions to the beta decay theory, the development of radiation detectors, and nuclear polarization techniques. She also conducted pioneering studies on the structure of the atomic nuclei, helped refine methods for separating isotopes, and so much more. She even wrote a textbook titled Beta Decay, which became a foundational reference for nuclear physicists in the future. By the early 1950s, Wu had become a professor at Columbia University, known for her rigorous teaching and her flawless experimental design. Around this time, two theoretical physicists, Sung-Dao Lee and Cheng-Ning Wang, proposed a shocking idea. What if one of physics' most sacred rules, the law of conservation of parity, was not actually universal? So, what exactly is parity conservation? Parity conservation is the principle that the laws of physics remain in the same in a mirror image scenario as in the original one. For example, imagine you're watching an object spin clockwise. In a mirror, it spins counterclockwise, but everything else looks perfectly normal. According to the principle of parity, both versions should follow the same physical laws. The universe, in theory, shouldn't care which direction is left or right. And so this idea is important because symmetry is the foundation of physics itself. It's what tells us that equations describing motion, energy, forces work everywhere and for everyone, that nature is fair and balanced. From Newton's laws to electromagnetism, physics depends on symmetry to predict how the world behaves. So if parity wasn't conserved, it meant something profound. That in certain situations, the universe itself could be asymmetric, preferring one direction over another. That would rewrite the most fundamental assumption about how reality operates. For decades, physicists believed that all physical processes obeyed this symmetry. It seemed impossible that the universe could prefer one direction over another. But Li and Yang suspected that in one specific kind of process, the weak nuclear interaction which governs beta decay, this rule might not hold true. Beta decay is a process that happens inside unstable atomic nuclei. When a neutron transforms into a proton, it releases an electron in a nearly massless particle called a neutrino. It's one of the ways atoms change their identity, literally turning one element into another. This transformation is driven by the weak force, one of nature's four fundamental forces. It's incredibly subtle, but essential. It powers the reactions inside stars and even the radioactive decay that warms planets. And it was here, in this delicate process at the heart of atomic matter, that Li and Yang suspected nature might quietly break her own rule. Hence, they needed an experimental physicist of unparalleled skill to prove it. They turned to Dr. Wu. In late 1956, Wu designed one of the most delicate and precise experiments in physics history. To fully understand her experiment, a simple example of parity conservation is that if a system is mirror symmetric, it should behave the same way as its mirror image, as explained before. For instance, a process where a particle spins one way and decays should be equally likely to happen in the mirror system, where the particle spins the other way, and the decay product should have the same intensity in both directions, up and down. This principle is violated by the weak nuclear force, which was famously demonstrated by the Chien-Shiung. She was able to use cobalt-60, a radioactive isotope that decays by emitting electrons. The goal was to determine whether electrons were emitted symmetrically or if there was a directional bias. To do this, she had to align the cobalt nuclei in the same direction, a challenge since atomic spins normally point randomly. Wu used liquid helium to cool the cobalt sample to a few thousandths of a degree above absolute zero, which, as learned in class, minimizes the thermal motion. Then, she placed it in a strong magnetic field to align the spins. When the cobalt decayed, she observed that more electrons were emitted in one direction than the other. Hence, so proved the universe does distinguish between left and right. Wu's result showed that parity is violated in weak nuclear interactions. Mathematically, parity transformation flips spatial coordinates. For example, in this equation, x, y, and z are all flipped into negative x, negative y, and negative z. If parity were conserved, the physical laws would be invariant, meaning the outcome of an experiment would look the same under this transformation. But Wu's data told a different story. The probability of electron emission in her experiment followed the equation. P theta equals 1 plus alpha cos theta, where P theta is the probability that an electron is emitted at an angle theta relative to the direction of the nucleus's spin. And alpha is an asymmetry factor, a measure of how strongly the electrons prefer one direction over another. If parity were conserved, then alpha equals 0, meaning electrons would be emitted evenly in all directions, perfectly symmetric. But Wu found alpha does not equal 0. Her results showed that more electrons were emitted opposite the direction of the cobalt's nuclei spin. The pattern was unmistakable. The mirror image of the experiment did not behave like the real one. In simple terms, the weak nuclear force, one of nature's four fundamental forces, distinguishes left from right. It breaks symmetry. This discovery was revolutionary. It upended a century of assumptions about symmetry in nature and opened doors to understanding the standard model of particle physics, the very framework of modern physics. Wu's experiment rippled across the world. It laid the foundation for deeper study of weak interactions, CP violation, and eventually the unification of the electromagnetic and weak forces into the electroweak theory, which later earned other scientists Nobel Prizes. Beyond physics, her methods, precise, quantitative, and experimentally elegant, influenced nuclear medicine, MRI technology, and quantum computing research, where understanding electron spin behavior is critical. Wu's contributions also carried profound social meaning. In 1957, Li and Yang received the Nobel Prize in Physics for the theoretical prediction of parity violation, but Wu, whose experiment proved it, was excluded. Her mission reflected the deep gender and racial inequalities in science at the time, and her story became a rallying point for equity in research. Yet, like many breakthroughs in nuclear physics, her work had complex consequences. The same understanding of atomic behavior that made modern medical imaging and cancer treatments possible also underpinned the development of nuclear weapons and radioactive technologies that pose environmental and ethical risks. The dual-use nature of her discoveries reminds us that scientific progress can illuminate and endanger the world at once. Dr. Wu's path was shaped by her upbringing in China, a culture that valued humility and hard work. Her father's belief in equality fueled her academic drive, and her mother's quiet resilience inspired her strength. Wu carried her Chinese heritage proudly, blending it with precision and curiosity of Western scientific inquiry, where she was able to spread her knowledge on the national scale. Wu's research inspired experimental replication around the world. In Japan, physicists at Riken Institute expanded her findings to study neutrino asymmetry. In Europe, work at CERN applied her parity violation principles to the study of Z and W bosons, the carriers of the weak force. Meanwhile, in her home country of China, new generations of scientists, many women, saw her as a national hero. She became a subtle bridge between East and West, between theory and experiment, between tradition and progress. Dr. Chien-Shiung didn't just conduct an experiment. She rewrote the symmetry of the universe. Through her, physics learned that even nature's deepest laws can break, and that discovery itself often comes from those brave enough to stand outside the mirror and question what everyone else assumes is true. Dr. Chien-Shiung remains a constant testament to brilliance, persistence, and the power of curiosity, a legacy that continues to shape science and society alike.